Right, so welcome everyone to this new short lecture on quantum statistical mechanics. So in the previous videos what we had looked at was first defining the quantum canonical ensemble, and secondly we also looked at basically two examples in the quantum statistical ensemble, the simplest examples in my opinion. And so the first one was the one-dimensional harmonic oscillator, and the second one was a one-half spin system in a magnetic field. Okay, so that's, in my opinion, the two easiest cases. You need really to pay attention to these examples. They come over and over again in statistical mechanics, so I do encourage you to study them and also realize that they are, although they both involve hyperbolic function, they are very, very different in the way they are treated. Okay, so now that we have done this, now I need to define the micro canonical ensemble in quantum statistical mechanics. And so again, it's a little bit like what we had before, so akin to the classical case. And what I mean by akin to the classical case is essentially we are extending the definition in the classical scenario to the quantum case. So we try to find the closest formulation for it. So akin to the classical case, we define the micro canonical ensemble as, and here that would be rho, so again that's the density matrix, and that depends on the parameter E, and this is equal by definition to E and divided by something that I call W of E. Okay, so that's how this is defined. And of course here I need to explain a little bit what these things are. So firstly, this thing here is a projection operator. Okay, onto the subspace. So what I mean by subspace is a subspace of the Hilbert space of states, if you will, onto the subspace at energy E. Okay, and this other object here, this one, we are going to see what it is, but this is basically a normalization factor. So we are going to do what we did for the canonical ensemble. So first we say that normalization is basically trace of rho, okay, which is egg here has to be equal to 1. And so what that means is that we have that the trace of rho, okay, is equal to, by definition, right, the sum over n of phi n, and then rho phi n, and this is for a basis, for the basis phi n. Okay, so is phi n or phi n in ket form, it doesn't matter really. N usually is belonging to integers, and basically that's it. So that's the usual thing for phi n. Now we choose, as before, okay, we choose phi n. So here I would put a ket notation as being a measurable state. Okay, so that's basically what we are interested in, so a measurable state, and so what that means that phi n will become something like hi AI, BI, etc. And that's it. Now if I actually say something like this, then what that means is that trace of row is equal to the sum over all possible values of HI, AI, BI, and all this. Okay, then I've got I need to have this particular object coming in, so that's HI, AI, BI, etc. And then here I need to put the projectors in. Okay, and once I get this, sorry, like this is like this, and then divided by W of E. Okay, then I can acknowledge a few things. So the first one is that this particular quantity here is delta HIE, and likewise here we get delta HIE. Alright, so basically here we get the same object, which is delta, a canonical delta of HI, and then you're kind of done. So at the end of the day, what we get is this is 1 over W of E, and then sum over HI, AI, BI, etc., and then delta HIE. Alright, so that's how we actually do it. Now the thing here that we are going to do further is remind ourselves that this has to be equal to 1. Okay, so there are a few things we can do from there. The first one is basically to say that the first thing is to say that so I need to take a new page here. So the first thing is to identify a probability. So we have the probability of HI, AI, BI given E would be equal to delta HI E divided by W E. Okay, so that's one first thing that we observe, and that's from basically applying the Kolmogorov axioms. Okay, so that's from Kolmogorov axioms. Okay, and the second thing that we observe after all is WE is equal to the sum over all possible HI, AI, BI, etc. of delta HIE. So that's the actual object that we are interested in. Okay, so W of E is this particular quantity. Now, what does that actually mean? That's an interesting bit that we want to know, is what this quantity represents. So this quantity is, if you look at, this thing. So this is a sum. This thing is a sum, in fact, over all possible measurable states for the system I'm interested in. Okay, and this bit here ensures that these states are at energy E. So at the end of the day, this is basically the total number, okay, the total number of quantum states, compatible with eigenvalue HI is equal to E. Now what we are going to see later is that this W here, which is the total number of quantum states, has a direct connection to what you may have seen about entropy. So in particular, there are things having to do with the initial Boltzmann formula, but also that it has a connection with what we have seen in classical statistical mechanics, namely the density of state. Okay, so we'll see that in the next video.